In previous videos, we saw how to transform y prime and y double prime, and these are transforms of derivatives. Now we're going to consider derivatives of transforms. Uppercase f of s is the transform of f, so it's the integral from 0 to infinity of e to the negative st times f of t dt. What we're going to do now is differentiate with respect to s. The derivative with respect to s of f of s is the derivative with respect to s of this integral from 0 to infinity e to the negative st f of t dt. But this isn't going to be like the fundamental theorem of calculus where the derivative undoes the integral, because we're differentiating with respect to s, but the integral is with respect to t. We're going to move the derivative to the inside of the integral, but now we've got two independent variables, s and t, and so the derivative becomes a partial derivative with respect to s, really of e to the negative st, and that's times f of t dt. The partial of e to the negative st with respect to s is negative t e to the negative st. So I'll write the negative outside. The integral from 0 to infinity e to the negative st times t f of t dt. This is the Laplace transform of t times f of t. So the derivative with respect to s of f of s is equal to negative Laplace transform of t times f of t, giving us the formula that you no doubt have seen. The Laplace transform of t f of t is the negative derivative with respect to s of f of s. We're going to use this in evaluating two Laplace transforms. One of them is the Laplace transform of t times the sine of t. When I think about applying transforms and inverse transforms to products and other interesting things, I start to interpret things in terms of clues. Where we have t times the sine of t, that t tells me I'm going to find a negative derivative. The function that I'm actually transforming is the sine of t. So this thing is going to equal the negative derivative with respect to s of the transform of sine of t, which is 1 over s squared plus 1. This derivative uses the power rule and the chain rule and evaluates to 2s over the quantity of s squared plus 1 squared. For this next example, we've got the Laplace transform of t e to the negative 3t times the sine of t. All right, breaking this apart. The sine of t is what we're actually transforming. The factor of t tells us we're going to find the negative derivative. What about the e to the negative 3t? Well, that's a shift. So piecing this together, we've got the negative derivative with respect to s of the transform of the sine of t, which would be 1 over s squared plus 1, with a shift because of the exponential. So instead, it's 1 over s plus 3, the quantity squared plus 1. All the little factors in there are telling us to do different things. It's basically a set of instructions. This is the negative derivative with respect to s. I would look at this as the quantity of s plus 3 squared plus 1 to the negative 1. And then use the power rule and the chain rule to get 2 times the quantity of s plus 3 divided by the denominator is s plus 3, the quantity squared, plus 1, whole thing squared. In case you're wondering, what happened to the negative? Remember, these I'm using the power rule, and the power is negative 1, so it's being offset. Now, what if t appeared with a power that was bigger than 1? Let's look at the Laplace transform of t squared times f of t. It's the Laplace transform of t times t f of t. That first t is telling us to find the negative derivative with respect to s of the Laplace transform of t times f of t. That second t in there is telling us to take, again, a negative derivative with respect to s. The result is the second derivative with respect to s of the Laplace transform of f, so of f of s. Where'd the negative go? Well, the negative from the one derivative and the negative from the other derivative multiplied together. This generalizes, denoting uppercase f of s as the Laplace transform of f of t for n values of 1, 2, 3, etc. The Laplace transform of t to the n times f of t is the factor negative 1 to the n times the nth derivative with respect to s of the transform f of s. To put this to use, we're going to find the Laplace transform of t squared times the cosine of t. This is equal to the negative 1 to the 2 times the derivative, second derivative, with respect to s of the Laplace transform of the cosine of t, which is s over s squared plus 1. Of course, the negative 1 squared becomes 1. And then the second derivative is, of course, the derivative of the derivative. So I'll write it down as the derivative, and then using the quotient rule, we have 1 minus s squared divided by the quantity of s squared plus 1, the quantity squared. I'll leave it to you to confirm that if you'd like. I want to show you the second derivative because something happens with rational functions, and it's often when we're taking a second derivative using the quotient rule. We've got u is 1 minus s squared, v is s squared plus 1, the quantity squared. And so u prime v is going to be negative 2s times s squared plus 1, the quantity squared, minus uv prime is going to give us plus the quantity of s squared minus 1. I reversed the order of that factor there, times 2 s squared plus 1 times 2s for the derivative of the denominator using the chain rule and the power rule, all divided by s squared plus 1, the quantity to the fourth power. The thing that I want to show you is this usually happens when I've seen a second derivative of a rational function, sometimes the first derivative. S squared plus 1 from the denominator shows up in every single term, and so we can cleanly divide that out and make our work a lot easier than it would otherwise be. I'll let you clean up all the rest of that and confirm that we have 2s cubed minus 6s divided by the quantity of s squared plus 1 cubed. Now let's put this to use solving an equation. Use the Laplace transform to solve the initial value problem. Y prime minus y is equal to t e to the t times the sine of t. I'll deal with this table of Laplace transforms in the instructions later. Our initial condition is y of 0 is equal to 0. Applying the Laplace transform to both sides, we get s times y of s minus y of s is equal to, and now we have t is telling me negative derivative, e to the t is going to give me a shift of sine of t, which is what we're actually transforming. So this is the negative derivative with respect to s of 1 over the quantity of s minus 1 squared plus 1. Factoring on the left-hand side gives us s minus 1 times y of s. The negative derivative on the right-hand side is going to give us 2 times the quantity of s minus 1 divided by s minus 1, the quantity squared, plus 1, whole thing squared. Notice the s minus 1's divide out, and we have that y of s is equal to 2 over that now hideous denominator, s minus 1, the quantity squared, plus 1, whole thing squared. We don't have an inverse transform that will handle this based on what we've seen so far. But there are tables of Laplace transforms just like there are tables of integrals. In the book I'm using, it's called Appendix C. And what we see is a function on the left and its Laplace transform on the right. A lot of these we have seen, some of them we haven't. What I want to do is try to match up the form of what we have to what we're seeing in the table. However, there's this s minus 1 quantity squared in the denominator of what we have. That's that shift. We aren't going to see a shift in the table usually, so we need to imagine that this is just an s squared plus 1, and actually we're going to have to imagine it's something just a little bit different. But I'm looking for a denominator that looks like s squared plus 1 the quantity squared, or something along those lines. And as I look through here in my table here, what I see is form number 25. And the transform version is 2k cubed over s squared plus k squared the quantity squared. We have here, without the shift, s squared plus 1 the quantity squared. And so that matches in form. So we'll note that for what we're working with, our k is equal to 1. The numerator is supposed to be 2k cubed. We have a numerator of 2, and so it is. So our inverse transform should be sine of t minus t times the cosine of t. However, we did have a shift, and since we have this s minus 1 here, we're going to throw in a factor of e to the t, and then say that's our function y of t. It's generally good form if you're using some sort of table, as long as your reader knows what reference you're using, to tell us, I used form number 25 in the table.